manage the rate of the student. This is like
Alright, guys, this is the first recording for our new topic, thermochemistry. Thermochemistry. So before I even start, I just did a demo. So why don't you look at the balance equations from the demo? We use barium hydroxide. That 8H2O means you have 8 molecules of water as part of that compound, plus ammonium thiocyanate. As you could see, if you feel the beaker feels very, very cold, that means the reaction is absorbing heat. The reaction inside the beaker is absorbing heat. Therefore, we are going to learn today the heat of the reaction. It is an endothermic reaction. It is absorbing heat. So we have barium thiocyanate, which is soluble in water. That's why it was not a solid. And then we have ammonia. This is a very strong smell you had. And we have some water molecules. So this is the balance equation for the reaction between barium hydroxide, octahydrate, and ammonium thiocyanate. As you can see, it is absorbing heat. Heat is on the reactant side. It is an endothermic reaction. Okay, objectives for today's lesson. You will be able to define enthalpy and relate the enthalpy change in a process occurring at constant pressure to the heat added or lost by the system during the process. We will be able to calculate the quantity of heat involved in a reaction at constant pressure given the quantity of reactants and the enthalpy change for the reaction on a mole basis. I need for you for homework, you will be completing Quest 19A Thermodynamics First Law. I already set on for this unit for you. You have a 19A, you have a 19B, you have a 19C, and you have a fourth one. So I already set up 4 quests for you for this unit. So for now, you can do only the first one. And I need for you to work on your pre-lab. You will be doing your lab next block day. Now, before we even start getting into any math, why don't we define some term? We have thermochemistry. Thermo, it is heat chemistry. So it is the study of energy changes that accompany chemical reaction. The study of energy changes that accompany chemical reaction. Thermo, heat, chemical, and then chemistry, we have the chemical reaction. What is energy? Energy is the capacity to do work or transfer heat. Capacity to do work or transfer heat. So let's see if we can derive the unit for energy. So we have work. What is work? Why don't we go down here and then I will derive it. Work is the product of force and distance through which the force works. So in other words, if we have to write a formula for work, you would write work equal force time distance. Okay, and then our force, what is the formula for force? Force equal mass times acceleration. Therefore, we can write that work equal mass times acceleration and time your distance. So why don't we go and replace everything by their units? So work equal equal mass. The unit for mass is kilograms times the unit for acceleration is meter per second squared. The unit for distance is meter. In other words, we can write work for the unit is kilograms times meter squared per second squared. And this unit, we will call it joule. Capital J, which is the SI unit for energy. The SI unit for work. It is joule. And you should also be able to convert joule into calories. Okay, 1 calorie equal 4.184 joules. Okay, 1 calorie equal 4.184 joules. When you see calorie with a capital C, it really means kilocalorie, which is 1,000 calorie. So you notice the unit for energy. What is system? System is whatever we are interested in. If I am studying the reaction of barium thiocyanate in a beaker with what did we use? It is barium hydroxide and ammonium thiocyanate. That reaction is my system. Okay, so whatever is outside that system is my surrounding. So the reaction going on inside the beaker is my system. The rest of it is the surrounding. Let me repeat. System is whatever I'm interested in. Everything outside that system is my surrounding. So heat, you know heat. Remember that heat flows from hot to cold. So if you open the windows, you are getting cold. You are not really getting cold getting in. You are losing heat. So this is the zero law of thermodynamics. Why is it zero? Because they already had a first one, a second one, and third one. So they went back and called it zero. Zero law of thermodynamics. Heat flows from hot to cold. And there is a flow of energy because of a difference in temperature. So make sure you know your kinetic energy, energy of motion, and potential energy is energy of position. It is energy stored in bond. So you know kinetic energy. I'm sure from physics, you know kinetic energy equal 1/2 times 1/2 meter second square. Is that right? Kinetic energy. This is our zero law of thermodynamics. We said the zero law says heat flows from hot to cold. That's the way heat flows. First law is a law of conservation of energy. Energy cannot be created or destroyed. Energy can only be converted from one form to another. It is our first law. And we will study the second and third law on the second part of the unit, chapter 19. The sum total of energy in the universe is constant. Alright, thermodynamics, we already said thermo means heat. Dynamic is motion. So you have motion, okay, and heat of motion. Internal energy is the energy, the total energy at constant volume. And we will study this later with the different symbols. So here are the symbols. So listen carefully. Delta E is internal energy. Whenever you see a delta, you already know it means change in. Okay, Greek letter, change in. It is final minus initial. Q is the symbol we will be using for heat. Q, lowercase q, heat. W is work, and then let's discuss their sign. If Q is positive, that's mean it is endothermic. Okay, the heat is getting in. It is endothermic. For a Q that is negative, heat had been released. it is getting out of the system. Exothermic. Let's go for work. The same thing. If work is done on the system by the surrounding, that work is positive. If work is done by the system to the surrounding, it is a negative W. Okay, what is state function? State function means a condition that does not depend on the path. Okay, it only has to do with, you can take your final minus your initial. Okay, state function. It doesn't matter what comes in between. For example, if I leave home to come here, it doesn't matter if I go through Olney. Doesn't matter if I go on Moncaster. It just matters that I left home, I got here, I get the change in that distance. Doesn't matter the path. Okay, state function is independent of the path. Enthalpy. We will be using the capital H for enthalpy. It is the heat at constant pressure. So delta E, internal energy, it is Q at constant volume. Delta H for enthalpy, it is Q at constant pressure. Q at constant volume, we don't really use it in high school. They use a bomb calorimeter. A bomb calorimeter is for measure heat at constant volume. In the lab, we will always be at constant pressure. So we will be calculating delta H, change in enthalpy. There is no device to measure enthalpy. So we will always have delta H, a change in enthalpy. So I need for you to look at this little graphic organizer right here. We will be using 4 different ways to calculate delta H. Okay, 4 different ways to calculate a change in enthalpy. And let's go ahead and start with those 4 different ways. We may not have time to cover all 4 today. We will not. But let's start with those 4 ways. Here's number 1. Okay, before that, this is the last 2 pages, I think I got them from honors chemistry from last year. So make sure you remember exactly the graph, an energy graph. The x-axis is reaction coordinate or reaction pathway or reaction progress. The y-axis is the potential energy. This is, you have your reactant here. This is the product. If the product has less energy than the reactant, that means energy had been released. Your delta H will be negative. If your product has a higher potential energy than the reactant, that means heat was absorbed, your delta H is positive. So your delta H is the difference in potential energy between the reactant and product. Delta H is from here to here. This is your delta H. From reactant to that peak, that's what we call activation energy. We will study this a lot next unit in kinetics. Activation energy is the energy needed for the reaction to start. That peak is called activated complex. Okay? So from reactant to that peak, this is our activation energy. From reactant to product, this is our delta H. This is activation energy and delta H. So you should be able to see from the graph if the reaction is endothermic or exothermic. Okay, activation energy without a catalyst. You know from last year, a catalyst is used to speed up a chemical reaction. How does it do that? By following a different pathway. So with the catalyst, you have a lower activation energy. That's why it is faster, by lowering the activation energy. Now, this is the first way we will use to calculate delta H. If you can have your calculators ready for us, please. First way is calorimetry. From the different ways to calculate delta H, number 1 is calorimetry. Let me see. In a coffee cup calorimeter, 100 ml of 1 molar sodium hydroxide and 100 ml of 1 molar hydrochloric acid are mixed. Both solutions were originally at, this is our initial temperature, we will call it Ti or T1. Okay, Ti for initial. After the reaction, the final temperature is this. So this is our TF. This is our final temperature. Assuming that all solutions have a density of, this is very important. This is the density. And remember, centimeter cube is the same thing as milliliter. Centimeter cube, milliliter. So it's 1 grams per milliliter. And a specific heat capacity of this. So symbol, we will use C subscript P for specific heat. And look at the unit, it is joules per grams degrees Celsius. Calculate the enthalpy change. They are asking for delta H. Enthalpy change delta H for the neutralization of HCl and NaOH. Assume that no heat is lost to the surroundings or the calorimeter. On your next lab, you will do the same assumption, or you will have a way to calculate the heat absorbed by the calorimeter. So, what formula do we use for the first way to calculate delta H? Let's start with Q first. Everybody write down that formula. Q, lowercase q for heat, equal what we call in AP or in college, MCAT. MCAT, mass time specific heat times change in temperature. Okay, MCAT. So therefore, Q equal, what is the mass of that solution? It is 100 ml NaOH, 100 ml HCl, give you 200 ml solution. And then because the density is 1 grams per milliliter, grams equal, okay, mass equal density times volume. Our volume is 200 ml, our density is 1, therefore the mass is 200 grams. Mass is 200 grams. Time, this 200, it is grams, because 1 milliliter is the same thing as gram. For water with a density of 1 grams per milliliter. Is that right? Okay, you don't see it. Let's do it. Okay, mass equal the volume, which is 200 ml, times the density, which is 1 grams per milliliter. The milliliter cancel out, we end up with 200 grams. So this is our grams. The specific heat is 4.184 grams, joules per grams degrees Celsius. When you do your quest, you had a list of constant. I need for you to find that list of constant and use exactly the constant you have from that list. Because there is one question, at least one question from the quest, where they use 4.184 and they add 2 more digits after this. So see if you have a list of constant that I gave you since last June. They add 2 more. 4.184, they say joules per grams degrees Celsius time the change in temperature, which is T final minus T initial. It is 31.3 degrees Celsius minus 24.6, which is 6.7. Thank you. Let me, okay, our delta T is 6.7 degrees Celsius, equal. As you can see, your grams will cancel out, your degrees Celsius will cancel out, your answer for Q will be joule. Can I have the answer, please? 5,606.56 joules. This is, let me do some erasing here to create some space. Okay, this is Q, but how do we express delta H? Even though they did not give you the unit of delta H, and in order to remember delta H, you need to express it in kilojoule per mole. Delta H, you express it in kilojoule per moles. That means we need to get our joules, delta H, and then we divide it by 1000, which will be our kilojoule, and then we have 1 mole of the HCl, 1 mole of NaOH produce 1 mole of your products also. Okay, so it is divide by 1000 give you 5.601. If we do significant figure, I should start with only 2 significant figure. It's 5.6. It is 5.6 kilojoule per mole. So this is your answer. All right, let's continue. It's still the same way, the first way to calculate delta H. We are still in calorimetry. Let me see if I need to do that. A 46.2 gram sample of copper is heated to 95.6. Okay, this is mass copper is heated to 95.4 degrees Celsius and then placed into a calorimeter containing 75 grams of water at 19.6 degrees Celsius. The final temperature of the metal and water is 21.8 degrees Celsius. Calculate the specific heat of copper, assuming that all the heat lost by the copper is gained by the water. Okay, we did a virtual lab last year where you took a piece of lead, you put it in calorimeter with water, and we solved some problems with that already. So this should be a review. So the heat lost by the copper should equal the heat gained by the water. So what do we have? I think we have enough to start with the water. Why don't we find Q water? Q water equal MCAT. Therefore, Q water equal, the mass of the water is 75.0 grams times the specific heat of water. They don't always have to give it to you. You need to know it is 4.184. Okay, the specific heat of water is not here, but it is 4.184 joules per grams degrees Celsius times the delta T water. It is, the water was at 21.8 and then the final temperature. Now the initial water temperature of the water is 19.6. This is Ti water. And then the final is 21.8. What is 21.8? Minus 19.6. 2.2. It is 2.2 degrees Celsius. So what is Q water? 690.36. Thank you. This is joules. This heat had been gained by the water. All right? But we said Q water equal Q, this is negative Q, copper, because the copper lost heat. The copper lost heat. Therefore, we can use negative 690.36 times the specific heat of copper we are solving for, specific heat copper, times the change of temperature of copper, which is the initial temperature of the copper was 95.4. This is T initial copper. The final temperature is the same because they are in the same calorimeter. It is 21.8. Is that right? Yes, 21.8. So what is 95.4 minus 21.8. Negative 73.6 degrees Celsius. Now we are solving for the Cp copper equal, it is our joules, which is negative 690.36 divided by negative 73.6, which is 0.19. This is specific grams, joules per grams degrees Celsius. This is the specific heat of copper. As you can see, the specific heat of copper is much lower than the specific heat of water. Okay, they told me it's not the right answer. Oh, multiply, you are right. We did not. Okay, that's why the unit was not. Okay, what is our mass of the? Yes, you are right. It is time. This number times 46. Where are we? Divide. We have to divide here by the mass also. Right here. It is 46.2. Okay, what is the answer? Okay, you gave me the right answer, but I did not put the mass right here. Thank you. Alright, so this is, let me repeat specific heat. The specific heat of copper is much lower than the specific heat of water. What does that mean? Copper will have a greater change in temperature by the application of the same heat. You apply the same heat to copper and water, copper will have a big change in temperature, and then water with a high specific heat will not change temperature much. As you can see, the change in temperature for water is 2.2. The change in temperature for the copper is 73.6, applying the same, using the same heat. That's why we said last year, when you walk by the beach, the water and the sand, they had been exposed to the exact same heat, which is the sun. The sand is very hot, the water is not that hot. Because the water has a high specific heat, it will take much heat to raise the temperature of the water than a metal that has a lower specific heat. The time is up. I'm not going to solve this problem, but I hope you pause the video, you try to solve it yourself, and I will show you the answer. So the answer should be negative 26 kilojoule per mole for this problem. So I hope you, if you need any extra help, you will watch the video and then you do your pre-lab and you do your first quiz. So enjoy the rest of your time. Bye bye.